Hi, I'm Stacey and welcome to my YouTube channel. And in this video, I'm going to be going over the block diagram and the project that I put together as a little demonstration for Robert Faranik's channel. And in that video that we collaborated on his channel, I go through how I made this block diagram. So if you want to see that process, you're welcome to check out the video in the description. To give you an idea of how this thing works, what it does, it takes the switch event, so if we have a switch change, and it'll send a packet on the network to tell your PC that the switch changed. And you can also receive packets. It will receive packets on the network and it will use those packets to change the LEDs. So that's basically what this does. And the demonstration of how it works is in the other video, at least showing you it behaving itself. So I am going to go through the blocks. We can easily see what's inside the block by right-clicking and going edit an IP packager like this. This code is all open source online on GitHub. I will also link that in the description. You're welcome to use the code as you please. So this is code that I have written over the past few years, primarily for this YouTube channel. And I have a couple of videos already explaining some of the older versions of this code. So for example, the code that's in this network port, this is the Ethernet one. It takes an AXI-Stream and it produces Ethernet from it. This one is already explained in a video from a couple of years ago. So I'm going to put that link in the description. And I'm not going to be going into too much detail about that one today. I rewatched a bit of it and the code is pretty much exactly the same. The only difference is that that is not UDP. It's just raw Ethernet and this is UDP. But I think in that case, it's just the header that's different. The UART as well is a module that I've already gone over in my channel in previous videos. So I will link that in the description. I think it's actually one of the first videos that I made was the UART video. One of the earlier ones. So I will not be going over that one today, but those videos are in the description. What I would really like to go over is the Snoop debug, because I feel like this is a concept that I haven't really covered on my channel. It does include a state machine, and it includes my favorite state machine. I love state machines, and I have over the years kind of settled on my favorite state machine that I do everywhere now. So I will show you the implementation of that, and I also will show you an arbiter. That is the first time that I've really done a dive into arbiters on this channel, and I quite like arbiters. I've written quite a few over the years and I really enjoy them. I enjoy writing them, I enjoy designing them. So I've never really touched on an arbiter. So I thought this would be a great opportunity for us to dig into something a bit new that we've never looked at on this channel before. So in this arbiter, I am actually using it as a debug interface. So basically there are two AXI-Stream Snoop ports, which means that it's got this little like magnifying glass icon that allows you to view the port without interfering, without messing with the communications in any way. So this is a Snoop port. We've got two AXI-Stream Snoop ports, and they get combined into one master AXI-Stream output that goes to the UART. And so basically what this can be used for is a means of debugging. So basically it'll take the packets, the stream packets that are on this interface, and it'll also tap them off and put them on the UART. And this is a really fun thing to do. I am going to open it up by right-clicking and going edit an IP packager, and here it is. So this particular one, let me just give you a run through of what Vivado does for these IP blocks. You'll take a look here and you see it gives you this interface to package it up, and it's quite nice because you can customize the GUI. So here I have two interfaces. So you can actually set this up to 4. If you look at ports and interfaces, I actually have it configured for up to 4 ports, and it's tied to the num interfaces parameter. So if I made this 3, then it should show 3. There you go. And if I made 4, then it'll show all 4. There you go. So you can actually, this is how Vivado makes these ports appear and disappear. The ports are actually tied to the enablement dependency parameter. So it's actually quite a lot of fun. I really enjoy making little GUIs for this. It's a fun part of it to just set up the customization GUI the way you want. So you can tell it how many ports it'll show. If you double click on this, that's this GUI. So that's the way you design what these GUIs look like. It's actually quite fun. I enjoy it. I'm going to take a look at the top level of this today. And as you can see, here are the 4 interfaces. So all 4 interfaces have to be there. They just won't be connected. And these are all inputs, even the ready. So because this is a Snoop interface, everything is an input. We don't have the back pressure for the AXI-Stream interface. If you need to know more about the AXI-Stream interface, then I do have a video on AXI-Stream, which I'll also link in the description. And AXI-Stream is a handshaking interface where you have back pressure. So the ready is the back pressure and the valid is the handshake. Basically, there's a ready valid handshake. It's not so bad once you get used to it, but it means that today, in order for the data to be valid, we need to be looking at ready and valid. And in our case, both of them are inputs because we are snooping the interface. So I have my 4 potential inputs and then the master AXI interface output. And you can see that this is not a Snoop interface, so we have the ready back pressure coming in and we are driving the data out. And that is the top level of this design. So how do I take 4 stream interfaces, I think I said 8, but 4 stream interfaces, and combine them into one? Because that is a question. Maybe that's something you want to do. So I'm going to go through that today. First off, we need to start thinking about the structure of the design. So whenever you have multiple inputs being combined down to one output, you need to consider a FIFO or multiple FIFOs, especially if you're having packets coming in. If you have packets that are coming in at the same time, then you need to be able to store them in their own FIFOs while you read out the data on the master interface. And that is what I'm doing in this case. So I have 4 FIFOs and every input interface has its own FIFO. This is the technique I use quite a lot. I use a generate statement, and the generate statement allows you to make as many copies of something as you need. This way I can make 4 copies of the same thing without having to actually copy and paste. I also have a generate statement video somewhere that I'll also link below. I think I need to make a list now because there's a lot of things that are happening that I need to write down. So that is how I am creating these FIFOs. And so what we're doing is we're taking these input ports, so for example the ready, and I'm concatenating all of the readies together. So this will be the LSB on the signal. So this signal is going to be 4 bits wide, and it's going to contain the 4 input readies that in a row, basically all combined into a bus. And then this genvar value will choose between them. So this 0th ready will be used, which was this guy, will be used in one of the FIFOs, and then the next FIFO will get the first ready, and then the next FIFO will get the second ready, and the next FIFO will get the third ready. This concatenate syntax is just allowing me to take the individual signals and combine them in the bus so that I can use them with this generate bracket I notation. These are all individual bits, which is why I can concatenate them like this. When I'm concatenating the data is already more than 1 bit. So this is 2-dimensional. So in order to concatenate the data, I concatenate it like this. And basically what I'm doing is I'm building a 2-dimensional array where the 1 dimension of the array is the 4 ports, and the other is the amount of data, the port input size of however wide the data is. And this will also work now with this I syntax. So this I really like, and this in particular is a system Verilog syntax. These 4 FIFOs need to have 4 outputs. So what we have is we have the 4 streams of data coming in to the FIFO. So now we need to have 4 sets of outputs, and that's what these signals are. So these are the output interfaces that allow me to choose which FIFO I'm going to read from. And that's the thing. So that's how come this is an arbiter, is I have to arbitrate between these 4 FIFOs. Now we need to decide between the FIFOs to decide which FIFO has data that we want to remove data from. First, we need to know which FIFOs have data, because if only one FIFO has data, then that's an easy choice, right? Just you use that one. So we start by looking at what FIFO has data in it. So the valid is an indicator. In this case, these are first word fall through FIFOs, which means if the valid is high, then it means that there is data in the FIFO. So I am using the valid as an indicator. So valid 0 is for the 0th FIFO, 1 is for the first FIFO, 2 is for the second FIFO. So we go through each of the valids, and if FIFO 0 has data, then the FIFO that we're going to choose is FIFO 0, and that choice is valid. If FIFO 1 has data, then the FIFO that we're going to choose is FIFO 1, and that choice is valid. If 2, then 2 and valid. If 3, then 3 and valid. So this is me going through the FIFOs in order of priority. So in this case, it's actually going to be a priority scheme where FIFO 0 will always have priority, and then FIFO 1, and then FIFO 2, and then FIFO 3. And now we come to the state machine. This is my favorite kind of state machine because I like to split up my state machines into asynchronous blocks, the asynchronous part and the synchronous part. I like to use an asynchronous block to decide what my next state's going to be, and then I register it into my current state. And the reason why I like that is because I like to know in the state what my next state is going to be. I like that, to be able to have that signal available to me. So I have a current state and I have a next state. And with an asynchronous always block, you can do this. You can create the next state signal now and know exactly what state you're going into. It's really, really useful to detect state transitions. If there was a clock here, if this was a clocked always block or a synchronous always block, then I would have to wait for the next cycle to be able to see what that state is. And I want to have it now. So that's why I use a asynchronous always block or an always block without a clock. So in the idle state, we wait until the next channel is valid. So that's this signal. So that basically is an indicator that one of the FIFOs has data in it. We don't know which one, but we do know which one because this signal tells us which one. But at this point, we don't need to know which one. We just know that there is something with data. So if there's no data, the next channel valid would be 0, which means that this wouldn't go high. So if we're in idle and there is a FIFO that has data in it, then we switch to the writing state. Otherwise, we just sit and chill where we are. It's important that we create these next states equals current states. You can also actually put this here at the beginning and it acts like a blanket next state is current state, if it'll let me do that. So you could also put that there. When we have data, we go into the writing state. And we are writing in the writing state until the last data beat of the output data. So when I'm in the writing state, in this state machine here, the only things I think about is the decision of when I move to the next state. So I don't have to worry about, in this state machine, the details of what I'm writing and when I'm writing it and all of that stuff. That doesn't happen here. All I care about in this state machine is building a framework for my code. I am going to use the state machine as a framework, and I'm building the framework. And the only things I care about in this state machine are the transitions to the next state. When I'm writing and I'm done writing. So that means my valid and my ready and my last is all high. That is the last sample of the AXI packet, because I need to write the contiguous packet. So I have to wait until I write out the entire FIFO, the entire packet from the FIFO, and then I can switch. And so these are the signals that I use to determine that I am done writing the packet. And then I go to the next state and I'm done. And the next state is last. And then that's one buffer state, and then I go back into idle again. I don't make any decisions here about any other signals. I love this method. It's such a nice, clean state machine method. It's so easily readable. I really like it. Okay, so we register next into current, because this is where the clocked register is, so that we can register the next state into the current state. So you say to me, well, Stacey, where is all of that writing happening? Like, we've made the state machine and there's only that many lines of code. There's that many lines of code and then we're done. So where is the writing? Well, it is that last little bit. So this is deciding what channel I want to read from and whether the channel is valid or whether any data is valid. And then this is deciding when I'm going to go into the writing state. And then the last step is this little bit, which is to read it out. So let's go through it. And this is why I like the state machine. It's because I can do this. So I can say when I'm in the current state idle and I'm going into the next state writing, so I can see the state transition as it happens. I'm in the current state idle, I'm going into the next state writing, then I register my next channel choice. And basically that's saying, okay, that channel that I decided I wanted to choose it, I am now choosing it. So this is pre-calculating what's coming up. And this is taking that pre-calculated choice and saying, okay, we're reading from this channel now. And then all I do is I mux this channel choice into my output data. So these are the signals that come from the FIFOs. So like that is this output signal here. And I basically just put that channel choice in the square brackets and use it to drive the output data. And what it will do is it will create the circuitry for me to produce this. So basically what it'll do is it'll use a mux. It'll create a mux where it says it will choose which FIFO to get the data from based on this channel choice, and it'll route that data to there. And so that's us writing out the data. So there's one last thing here, and that is to route the ready back to here. So because this has back pressure, so this ready signal is a back pressure signal. Let me just go back here. This interface has a back pressure signal, so that's what this T ready is. And that means that I have to route this back pressure that I'm receiving into the module. I need to route that to whichever FIFO is currently being read out. So it needs to come into whichever FIFO I'm reading from. And the way that we do that is I'm using an always combinational always block here, which is the same as this guy. Actually, that's two different ways of doing the same thing. So it starts 0 so that they're all 0 by default. And then the specific channel that I want to read from gets that ready signal fed back. And that's only during the writing state. And otherwise, the rest are 0. And this, I think, is where arbitration can get a little bit hairy. There's two places where it can be a bit difficult. One is when you have back pressure and you have to route the back pressure into the FIFOs that you're reading from. So you have a back pressure signal that comes in and you have to apply that back pressure back into whichever FIFO you're reading from. And the other issue is maintaining the packet integrity, where you read a full packet out from the FIFO and then you move on to the next channel. And so those are the two places where I feel like it can go a bit wrong. And so one of the important things is maintaining the clean switch between FIFOs. And that's what this channel choice is doing. The channel choice signal is the clean switch that says, okay, I'm going to switch from this FIFO to this FIFO now. And that's why when I'm ready to go into the writing state, I switch channels at that point and I have a nice clean transition into the next FIFO. And when my packet is done, then I can transition out of that state. And so this is how I determine, that's how I ensure packet integrity. And I use this ready input to route the signal back into the FIFO that I'm reading from. And so that is this module. It is quite a complex module to get your head around. And I think that one of the important distinctions is understanding the differences between this combinational always block and these clocked always blocks. I think understanding your differences between your synchronous and asynchronous logic is really important. I'm going to link a video in the description and also there about the differences between synchronous and asynchronous logic and why it's so important, because that is an extremely important distinction that you need to have in mind when understanding what's going on in modules like this. I think that's going to be it for today. So thank you for joining me today, and I hope that you'll stick around. I really like to focus on making videos that are high quality and making videos that I'm passionate about. And sometimes it takes a while to get to that point where I have a topic that I really like and I'm passionate about it, and I feel like I can explain it in a concise and precise way. And so I think that and that is one of the reasons why I'm not making that many videos as often. You're welcome to comment if there's anything else that you would like me to focus on, or a video that you would like me to make in particular. But I really want to ensure that I am not just putting out content for the sake of content, and that it is really going to be useful and it's going to be presented in a clear and concise manner. And so that's why I'm not posting as often. I will post when I get to the point where I can make a video that I feel like is a video worth making, if that makes sense. So I hope that you'll understand and bear with me as I continue to attempt to make videos on my channel, and I appreciate your support. Thank you very much, and thanks for joining me today. Bye.